Okay, so in the last lesson in chapter 3, we learned how to prove triangles are congruent. So today in the next lesson, 3.3, we're going to take that a step beyond and learn this thing called CPCTC. And this is something that you are going to use so much for the rest of your geometry career. So this lesson is huge. We're also going to do a little bit of review of circles, and you're going to see how circles start to come into play as well in some of our proofs. So we're just going to make sure we understand what CPCTC is all about today, and then remember the basics about circles. So here is our warm-up, just a little throwback to yesterday. So you're given our triangle here in our picture, given segment MH is congruent to segment TH, angle MHA is congruent to angle THA, and we are going to try to prove that triangle on the left, MAH, is congruent to the triangle on the right, TAH. After yesterday's lesson, you should be able to do this. So why don't you pause your videos and write this proof. All right, so our first step is our first given. Segment MH is congruent to segment TH. And that is given, and I'm going to make sure that I mark my picture. Okay, now the next one was angle MHA is congruent to angle THA, and that was also given. Now be careful, angle MHA is this angle up top, angle THA is this other angle up on top, making sure that we mark those appropriately. All right, now I'm trying to prove that the triangle on the left, I'll highlight it for you, MAH is this one, is congruent to the triangle on the right, THA, right here. Okay. I'm trying to prove those two triangles congruent. Now, as I was marking that, as I was going through, I noticed that I did have one side that was already marked congruent. I had an angle that was already marked congruent. And then I have this side in between the two triangles that overlapped colors, right? They were both used. It was used in both triangles, and we learned yesterday that this was called the reflexive property, right? So segment HA is congruent to segment HA, and that was by the reflexive property. And now it looks like I have segments, angles, segment. So it looks like I'm ready to write my proof statement. Step 4 here, triangle MAH is congruent to triangle TAH. And the reason is side, angle, side. And here are my 3 steps that I used. The first step was a side, the second step was an angle, the third step was the other side. So 1, 2, 3 goes in the parentheses. All right, so hopefully that was review from yesterday. You did pretty good. You mastered that, no problem. So now we're going to take it a step further. Now this is the exact same picture, right? And we have our given here that triangle MAH is congruent to triangle TAH, exactly what we just proved. But now I want to know, what else do we know? So we just proved that these two triangles were congruent, right? That one was congruent to this one. We just did the whole proof for it, so we already knew that. What else do I know? Now, in our given, right, we knew that these were congruent, and we knew that these were congruent, and we proved that this was congruent using the reflexive property. But what else is there? Well, if I know that my triangles are congruent, then don't I know that all the corresponding parts are congruent? I only needed to use some of them to prove the triangle is congruent, but now that I know they're congruent, I know that all the others are as well. So that means that I know that MA is congruent to AT. Segment MA is congruent to segment AT. I also know that this angle M is congruent to angle T. Those are corresponding, right? Oh, I also know that these angles in the middle here, now I have to be careful, I can't call it angle A, right? But I could call it angle MAH is congruent to angle TAH, right? So I know that all of the corresponding parts are congruent once I have the congruent triangles. So this is that big idea of taking our congruent triangles and going a step beyond. This is what we call CPCTC. Corresponding parts of congruent triangles are congruent. So here's the thing. This is super useful because look at all of the different congruent steps that we could come up with once we prove the triangle is congruent. We have so many. So it will help us so much. It's very common to write CPCTC or this reason in more than one step of a proof because you can get so many things from it. However, the biggest mistake is that you think you can jump to this right away, but be careful. You must be given or prove that the triangles are congruent before you can use CPCTC. Must prove or be given congruent triangles first. Be careful. Okay. And the other thing is we want to make sure that you're saying this right. The corresponding parts of congruent triangles are congruent, not congruent parts of congruent triangles are congruent, right? If we already knew they were congruent, you wouldn't need this theorem at all. So it's the corresponding parts of congruent triangles are congruent. Now you'll notice that we don't have an if-then form for this. And that's why it's tricky to make sure that you have what you need before you use this. And that's why I put those words in blue there. You must prove or be given that you have congruent triangles before you can use this idea of CPCTC. But there is no if-then form, so that's kind of nice. All right. So we'll get back to this CPCTC idea in a minute, but for now, let's go ahead and review some things about triangles. All right, so first of all, this point in the middle of the triangle, about circles, there we go. So first of all, this point in the middle of the circle right here, we call the center, right? Now the center of a circle is very important. We label the circle by the center. So we would say circle O. When it's circle O, I always think it's funny. It looks like, ooh, okay. But this is the symbol for circle, right? And we label the circle by its center. So when we label it, we say circle O, that's telling us that, yes, this is a circle, but also that the center of this circle is the point O. And that'll help us a little bit later on when we hit circles even harder. But for right now, that's just a good thing to know is that when we label this circle, we label it by the center. Notice I put outside here the circle I put way on the outside, and that's something just to point out that the circle is only considered the ring around the outside, not everything filling it in. Again, that'll become more important later on when we do circles even more, but just to get that idea in your heads now is that the circle is only that green ring around the outside, not the whole area that's on the inside. All right, so we have a couple of segments that are marked in our circle here. One segment that we have marked is the segment QR. And notice that that segment QR is passing right through the center of the circle. We call that a diameter. Hopefully that's review for you, right? Okay, and then we have a separate segment here, the segment OP. And notice that's starting at the center and going to the circle. That we call a radius, right? So if it's going all the way across the circle through the center, we call it the diameter. If it's starting at the center and just going to the ring, we call that the radius. Okay, now there are a couple of formulas that we always have when it comes to circles, and hopefully you remember them. So first formula is for the area of a circle. The formula for area is pi r squared. I should write A equals pi r squared, right? Okay, pi r squared. And remember for area, units are always squared. Radius squared, unit squared, keep in mind, okay? Now we also have circumference of a circle. Now remember that circumference is basically like the perimeter, right? the length around the outside. So the circumference has two different formulas. Hopefully you remember them. One of them is 2 pi r, or you could think of it as pi d. So 2 times pi times the radius, or pi times the diameter, since 2 times the radius equals the diameter, right? So either one. But do not get them mixed up. Know the difference. Which one is the area? Area is units squared, radius squared. Circumference is no squareds, right? 2 pi r for circumference. All right. So that's our basic vocabulary. Now, once we talk about this idea of a radius, most of the time it pops up as we're talking, right? That you can have a radius in more than one place in the circle, right? But that since this is the very center of the circle, L is the center, then the distance from the center to the circle, no matter which direction you go, is always the same, right? That's kind of the definition of a circle, is where the distance from a single point is the same, any direction. So the question is, well, why would we say that segment KL is congruent to segment LM? Well, the reason is because if they're both radii of the same circle, then they have to be congruent. And that's a new theorem for us. So we have a theorem that says if two segments are radii, that's the plural of radius, right? More than one radius is radii. If two segments are radii of the same circle, then they are congruent. If two segments are radii of the same circle, then they are congruent. Now notice we have to say that they're radii of the same circle, right? Think if I could draw a teeny tiny little circle here. Whoops, I didn't mean to draw it in crayon. Here we go. With my center here, and I put a segment there. Is this segment the same length as the one as LM? The answer is no, right? I can't just say if two segments are radii. This is a radius. Let's call this OP. OP is a radius. LM is a radius, but they're definitely not the same length because this circle is way smaller. Okay, so that's why you have to say that these two segments are radii of the same circle when you're using this theorem. Now, you're probably wondering, when we're using our if-then form, we always have to, whatever's in our if part here, we have to say in a statement. Well, so this says if two segments are radii. Now, if I look at that picture, can I tell that those two segments are radii? I absolutely can. If a segment looks like it's starting at the point L and ending at the point M, then it is, right? That's something I can assume from the diagram. So we'll just make a note here that you can assume radii from a diagram. And we'll put can assume radii from a diagram. So that means if I was going to write this in a proof, right, if KL congruent to LM was going to be a statement in my proof, and I was going to write if two segments are radii of the same circle, then they are congruent for the reason, then the step before that would have to say KL and LM are radii of circle L, right? And the reason would be assumed from diagram. And then I could say that KL is congruent to LM. So remember, just kind of like with vertical angles, this is kind of a double step. Whenever you want to use this new theorem, you got to include the assume from diagram step first. All right, so we got a new theorem here that's really helpful, along with CPCTC. Man, we got a whole bunch. Okay, so let's start doing a couple of proofs, making sure you know how to use these brand new theorems in our proof. All right, so in our picture here, we're given MH is congruent to TH, segment HA bisects angle MHT, and we're going to try and prove that segment MA is congruent to segment TA. Hopefully this is looking familiar to you because it looks very similar to the warm-up, so I'm hoping that you could pause your video right now and write this whole proof. Ready, go. All right, so our first step will be to write down our givens and mark our picture. MH congruent to TH, given. Second step, HA bisects angle MHT. Now this needs a little bit more breaking down this time. I'm trying to get to MA is congruent to TA, right? Right now, I'm only given that this segment bisects this angle. So I better include a second step here, or a third step, I should say, where these two angles are congruent. So angle MHA is congruent to angle THA. And the reason, if an angle is bisected, then it is split into two congruent parts. All right. Now, I'm trying to get that these two yellow highlighted segments are congruent. I'm not sure how I'm going to do that just yet, but I do know that with the reflexive property here, I can say that segment HA is congruent to segment HA, in which case I'll be able to prove my triangle is congruent just like I did in my warm-up, right? So I'm going to add that step in, segment HA congruent to segment HA, and that was the reflexive property. And again, the only time I have to include this reflexive property is when I'm going to prove some triangles are congruent. But now that I have that, now I can prove, step 5, triangle MAH is congruent to triangle TAH, making sure I have those things lined up in the correct order. And the reason is side, angle, side, right? Step 1 for a side, step 3 for an angle, step 4 for a side. So 1, 3, 4 this time. I had an extra step after instead of my like my warm-up. Okay, so now I just proved that the triangle on the left was congruent to the triangle on the right. Oh yeah, now I can use my idea of CPCTC to say, well, now that I know those two triangles are congruent, then all their corresponding parts must be congruent. And since I was very careful about the order that I wrote my letters in, I noticed segment MA has to be congruent to segment TA, right? Because those are the corresponding parts in that set of congruent triangles. So step 6 will be MA is congruent to segment TA. And the reason is corresponding parts of congruent triangles are congruent. Now, I do want you to write this out, okay? You can use the symbols like I used, but please do not say CPCTC just yet because your brain has not recognized what those letters stand for yet, and you need to be making sure that you write this because your self-check here, in order to be able to use corresponding parts of congruent triangles are congruent, you have to make sure that you have proven congruent triangles before you can use this idea of CPCTC. So you must write out CPCTC using the words and not the letters, not just the letters. Okay, you can use the symbols like I did for congruent and triangle, but you have to write that out because your self-check is to make sure that you understand what those letters stand for right now. All right, that was a practice proof using that idea of CPCTC. So yesterday we learned how to get up to that triangles congruent step. Today we're going to take it one step farther. What else could you say after you get congruent triangles? But make sure that you still have that congruent triangle step in your proof before you take it a step farther. Okay, well, let's see. How are we going to use circles then? So here we go in our new picture here, and all you're given is that you have circle O. So again, remember that that means that yes, this is a circle, and that O is the center. And we're going to try and prove that segment HT is congruent to segment DG. So I am going to start off my proof with my one and only given, which is circle O, given. All right, Now, I'm trying to prove that segment HT is congruent to segment DG. Hang on. There isn't a segment DG. Well, that's weird. Now, do I know that there's a segment there even if it's not written? Well, sure. If I have 2 points, I can always connect them with a segment, right? So whenever you have a picture and it doesn't include segments that you want, as this might happen now, we're getting into more complicated situations. Say, I want to have a segment in this picture, but it's not there yet. You can always draw one in, and I wanted to show you how to do that. So I could do that as a step of my proof, but I need to make it a step. I need to say, draw segment DG. And the reason as I was talking through it, right, I actually said it in if-then form. If there are 2 points, then there's a segment between them. Okay, so make sure that you write that in if-then form like everything else we need to do here. If there are 2 points, then there is a segment between them. Now be careful, I know your answer key does not write that in if-then form. They say 2 points determine a segment or something like that, but please write that in if-then form because we're just wanting to make sure our brain is in that habit of writing things in if-then form. Now whenever you add in a line like this is called an auxiliary line. Now, you don't really need to know that so much, but if the book ever talks about auxiliary lines, that means it's an extra. It's one that wasn't in their picture to start with. And so that just means something that you draw in. And the way to do that is to say draw whatever segment you want, and then you use this good if-then form for drawing in that segment. Okay, so getting back to our proof here, we're trying to prove that segment HT is congruent to segment DG. Now, after we drew in that line, I'm hoping that 2 triangles are jumping out at you, and I'm hoping you can think about some of our previous theorems and maybe one of our new theorems that will help us prove those 2 triangles are congruent in order to use CPCTC. Why don't you pause your video and see if you can do it? All right, so the next thing that I would do is I see that segment OH, segment OT, segment OG, and segment OD are all radii of circle O, right? They're all coming from this center point and going to the circle. And that we can assume from the diagram. I can assume that a line goes through a point if it looks like it does in the picture. So assumed, from diagram. All right, now I had to say that they were radii before I could say they were congruent, but now step 4, I can actually get all of them in one shot. OH is congruent to OT, is congruent to OG, is congruent to OD. They're all congruent to each other, right? OH congruent, I'm gonna actually give it 2 lines because my highlighting, it looks like that's only 1. Okay. Congruent to OT, congruent to OG, congruent to OD. And our new theorem was if segments are radii of the same circle, then they are congruent, right? Make sure you have those words of the same circle in there. Okay. If you want to make sure that you did everything, you included what you needed to, remember, do your if-then check. The if part needs to be a step before that. It says if segments are radii. Do I have radii as a step before that? Yes, I do, right? I could even just go through and highlight it really quick for you. So in my if part says segments are radii. Here I have segments are radii, so I'm good there. In the then part, I am saying then they are congruent, and that's what I'm saying in these steps, right? I'm saying congruent in the step right now. Make sure that if whatever is in the if comes before, whatever is in the then is what you're saying in this step. I've got it in the right order. I'm good to go. All right, so I've got a bunch of sides marked congruent. I'm trying to get the last pair of sides congruent, so I don't think I'll be able to use that to prove my triangles. So what I need is the angle in between those sides, right? what I need is this angle here to be congruent to this angle here. Hang on. Those are vertical angles. Step 5, angle hot is congruent. Oh, now hang on, Mrs. Carrivo. Lay it back up. Angle hot is vertical to angle dog. Remember, we have to include that assumed from diagram step before I can say they're congruent, just like our radius theorem, right? So don't forget that. I almost did, but I would have got it when I did my if-then self-check, right? So here's step 6. Now I can say angle hot is congruent to angle dog if two angles are vertical. Oops. Then they are congruent. Okay, and again, my self-check here, right? The if part says if two angles are vertical. Here I have the angles are vertical. And my then part, what I'm saying in this step is then they are congruent. And that's what I'm saying in this step. So my if then is working out. I included everything I needed to. Okay, so now I have, let's see, side, angle, side for my two triangles. So we are good to say step 7, triangle hot is congruent to triangle dog. Now here, this is a little tricky, right? It is side, angle, side, but I got 2 pairs of congruent sides from the same step. And then step 6 was my angle. So I need to say side, angle, side, and I'm going to write the number 4 twice. You could write it 4, 6, 4 if you want to keep them in that order of side, angle, side, or you could write 4, 4, 6 if you want to, but you do need to always include 3 numbers. So if you get 2 congruent things from the same step like I did there, you have to list the number twice. Okay, so I just proved, oops, this is what I wanted. This triangle up here is congruent to this triangle down here. And now I believe I can use my idea of corresponding parts in order to get those segments that I want to be congruent. So last step here, step 8, segment HT is congruent to segment DG. And the reason is corresponding parts of congruent triangles are congruent. And they are corresponding first and last. I'm good to go. Those are the corresponding segments there. And I made sure that as I did my self-check here, as I use my CPCTC, right, it says parts of congruent triangles, and I have proven my triangles congruent before I used that step, so I'm good to go. All right, really good practice there using our radius theorem and our idea of CPCTC. So we got some good practice there. So just to wrap it up, remember that CPCTC stands for corresponding parts of congruent triangles are congruent, and we are going to write out those words or using the symbols in our proof. We're not going to just use the letters until we really know what those letters mean. You must prove or be given that the triangles are congruent first before you can use CPCTC. Okay. We also learned that all radii of a circle are congruent. Make sure that they are in the same circle, and you can assume radii from a diagram. And then if you need to draw in any segments into a proof, you can. Just make sure you use that good if-then form that we learned in that last proof.